Welcome to the Artificial Intelligence course, a complete introduction. The lesson today will introduce to you one of the most recognized techniques in AI, artificial neural network. Honestly, I think that many of you have heard about neural network before joining this class. But don't you know that neural network has already been studied since the mid-20th century and it was not really successful until the years 2000? In fact, thanks to the availability of data and the support of powerful computers, neural network is really coming back to become a state-of-the-art in machine learning, and nowadays it has been receiving more and more attention in studies, researches, and many real-life applications. Now, let's start with some basic concepts of artificial neural network. First of all, to give you some basic ideas of artificial neural network, let's look at its original version, the biological brain. As a matter of fact, our brain may be the most important mechanism in our body. It allows us to analyze what we sense and to make decisions. For example, we can see everything visually because we have eyes. But actually, eyes are just some kind of sensors which receive optical information and transfer this information to the brain. Then, the brain, as a processor, will analyze and extract useful information from this input to make appropriate decisions. For example, when you are driving, you have to read traffic signs in order to control your vehicle correctly. And sometimes, information needs to be processed in milliseconds. So, how can our brain do this? Here is the answer. Our brain is composed of 100 billion nerve cells called neurons. Neurons allow processing information by making an extremely large connected network, and this kind of network is called biological neural network. To give you an idea of how large is the network, let's imagine that, in average, a human brain has around 86 billion neurons, and each of them may connect up to 10,000 other neurons. This makes approximately 1,000 trillion synaptic connections. Can you believe that? Now let's look at the detail of a neuron. You can imagine that each neuron is like a processing unit with input, output, and a processor. Particularly, information comes to the neuron's dendrites, and the nucleus processes this information in terms of an activation. Finally, the axon is responsible for transmitting signals out of the neuron. Precisely, if you look at the image, here are the dendrites of the neuron, which receive signals from other neurons or from other cells, imagine from eyes, for example. And here is the nucleus, which is like the controller. Next, the body of the cell is called soma. It contains and keeps the nucleus functional. And the axon stays here. It is considered as the output of the neuron. Then, signals are transmitted through the axon by this way to go to other neurons or cells, for example to this one, so the two are connected together. And this new one, again, may be connected to other neurons, and so on, building the complete nervous system. For example, this neuron may output signals to cells controlling arm actions, or this one may be to control legs. So that is the idea of how biological brain works to process information. Indeed, this is not a biological class, so I could not give you so much detail of a neuron, but you just need to remember that a biological neural network is composed of so many connected neurons, and each neuron has some inputs, an activation or controlling unit, and one output, that's all. Inspired by the biological neuron, we would like to design the artificial neuron as follows. First, we have the neuron at the middle. In one side, we have the inputs called H1, H2 up to Hn. So we have n inputs for the neuron. However, we want to add another input. H0 is always equal to 1. As you already learned from previous lessons about linear regression and logistic regression, You know that this is called the bias unit, okay? Next, we would like to put a weight for each of these inputs. So phi0, phi1, phi2 up to phin. So we have vector x consisting of x0, x1, x2 up to xn is the input vector. And similarly, vector phi is the weight vector consisting of weights or parameters to learn. Then, in another side, we have the output of the neuron y equals f of x. It means that the output of the neuron is a function of x and parameterized by phi. Finally, at the center of the neuron, we need an activation function which computes the output y based on the input x and the parameter phi. To illustrate the idea, let's remind the biological neuron. You can imagine that the input x and the weight phi are similar to the dendrites of the neuron, whereas the activation function is like the nucleus, and the output y is the axon of the neuron. Okay? It's simple. Usually, activation function is often a logistic function of phi.x. So we got g of phi.x equals 1 over 1 plus e to the minus phi.x, where e is the Euler's constant. As you have already seen this function in the lessons about logistic regression. Indeed, logistic function is often proposed because of its beautiful properties, but there are also alternative choices such as the rectifier function that I really encourage you to spend time reading about it. In this case, we will use a logistic function as is very common. Just to remind you what is a logistic function, let's look at the graph of the function g of z equals 1 over 1 plus e to the minus z. It has a sigmoid curve, is bounded between 0 and 1, with middle point is 0.5 when z equals to 0. Okay? Now, I would like to give you a simple example. Imagine that we have a neuron with a logistic activation function g, and this neuron has two official inputs, x1 and x2. For example, x1 equals 2 and x2 equals 5. As that official inputs, because we want to add a bias unit x0 to the input vector like this, and remember that x0 is always equal to 1. Next, we suppose that the input weights are some values like this. phi0 equals 2, phi1 equals minus 1, and phi2 equals 0.3. So we have the input vector x consisting of 1, 2, and 5, and the weight vector phi consisting of 2, minus 1, and 0.3 respectively. Then, the output of the neuron is f of x, which equals g of phi.x. Okay? Now let's try to calculate this output f of x. First, let z equal to phi.x, which is equal to phi0 x0 plus phi1 x1 plus phi2 x2. According to the example, this equals 2 times 1 plus minus 1 times 2 plus 0.3 times 5, which is equal to 1.5 at the final. So, if we apply this value of z in the equation of g, we have g of phi.x equals 1 over 1 plus e to the minus z, which is approximately 0.82. Therefore, we say that the output of this neuron given such inputs is 0.82. Okay, I hope that this very simple example can give you the idea of designing an artificial neuron. Indeed, if we use a logistic function as the activation of the neuron, then the neuron is no different than what you have learned in logistic regression, right? But the beauty of neural network is that neurons are interconnected to make a powerful processing network. In the next lesson, I will show you different neural network architectures from simple to complex. Thank you for your listening.